This is our final video, and it's on the second fundamental theorem of calculus. We want to talk about what is it and why it is important. You should know that this fundamental theorem of calculus is considered by many as one of the greatest achievements of the human mind. One reason for this, well, there's several reasons. One reason is it connects the idea of area and rate of change, the idea of integral and derivative. But probably one of the more interesting reasons is that it allows us to actually create new functions. So before we had four elementary functions. We had these power functions like x to the n, exponential functions like e to the x, logarithmic functions like ln of x, and then the trig functions like cosine of x and sine of x. And these are what we call the elementary functions. And most functions that you experienced so far in mathematics courses have been made from one of these four functions by adding, subtracting, multiplying, dividing, and composing. Once you introduce the idea of integration, you can actually create new functions because you can start to ask questions like, well, what's the integral of x dx? Well, that gives you a new function, and we know we add one to the power, so you get x squared, divide by it, 2, plus any constant. But there's some integrals, indefinite integrals, we can't actually integrate, like e to the, let's do x squared dx. It turns out that this cannot be represented in terms of elementary functions. And so what happens is when we start looking at this second fundamental theorem of calculus, it's going to give us a way to create a new function whose derivative, so we'll be able to create this function f of x, whose derivative, and let's call it actually, I'll make more sense here, we'll create this new function, let's use red. Second fundamental theorem of calculus, so let's create this new function f of x, with this property that f prime of x is equal to e to the x squared. And it'll turn out that this f of x is not, or we're not able to represent it in terms of these elementary functions. So it's a whole new type of function. I always tell students, like, in the zoo of functions, this is like sort of discovering, the dinosaur, the existence of dinosaurs. But it's even better because it's actually, the way that we discovered it is using sort of more modern ideas of functions, and we're needing to model more modern ideas, such as probability theory and insurance, or trying to model things involving electricity or magnetism. So these functions naturally pop up in those sorts of arenas. So let's take a look at the second fundamental theorem of calculus, because it's kind of complicated at first to understand what it's actually saying, but it says, hey, give me a function that's continuous. So give me a function f such that you can draw it without lifting up your pen or pencil. Then this new function, capital F, defined by this, right? So f of x equals, and a can be any number, and x is, of course, your variable. And then we're going to use t here because we don't want this x and this x here, in some sense, or these two variables to coincide. We don't want them to be the same, otherwise it gets a bit confusing. So we let it be t, so f of t dt. And so we know that this new function we create is continuous, and it's also differentiable, and it has the property that f prime of x is equal to f of x. So real quick, let me just give you a real simple example. So let's take the function we did before, like x. So we can create f of x to equal the integral, and let's just let this bottom limit be 0 to x. And then instead of letting x be here, we'll let it be t, so t dt. And think about what this function actually represents. It's just counting up the area underneath the curve of basically y equals x. But if we want, we can call this t. Let's call this t. And since it's just y equals t, here's my output y. And it's going from 0 to x, so let's change colors here. So 0 to x. And so what this integral is giving me is this area in blue, right? I say integral, you say area. And as you change x, of course, the area this function will change too. So if you move x out to the right, f will get bigger. If you move fx to the left, it's going to get smaller. And so that's what this function represents. So let's take a look at some examples down here and kind of get the idea. So we want to understand, why is it important? And I already kind of alluded to the fact that you're able to make these sort of new functions that did not exist before. And we want to answer these sort of two little questions here. How do we evaluate these functions? And then two, how do we take their derivatives? And so it's actually really quite simple because the fundamental theorem tells you how to take their derivatives. Let's look at an example. So here's our first example. And we want to find f of 5 and then find f prime of 5. And so what we have is here's our function. And let me just copy it down below here. And so I have f of x equal to the integral from 1 to x of 2t dt. And if I want to figure out what f of 5 is, it really should not be that bad. So just plug in. So evaluate f at 5. So f of 5 would be equal to, so every c in x, you put a 5. So this is equal to the integral from 1 to 5 2t dt. And I really don't need a calculator to do this because I can do this indefinite integral. So the integral of 2t is just t squared from 1 to 5. So I just find the antiderivative of 2t. And then I plug in the upper limit, which is 5. So 5 squared minus, and plug in the lower limit, which is 1 squared, which is equal to 25 minus 1, which is equal to 24. So when you plug 5 into this new function, capital F, right, capital F of x, you get out 24. And to find the derivative is even simpler. So f prime of x, the fundamental theorem of calculus tells us f prime of x is just equal to this integrand right here. So let me use red. So this integrand when you plug in x. So it's just equal to 2x. Right, because remember, the second fundamental theorem of calculus says if f of x is equal to the integral from any number, a to x, of ft dt, then I know that the derivative of capital F is just equal to little f evaluated at x. Let's take a look at the next one. This next one's a little bit harder. I can't do this one by hand. And so on this one, you can see here's my new function. And I want to answer similar questions. So I have this, let's use black. I have this capital F of x. I'm creating this new function. And I'm going to make it the integral from 0 to x of t plus 1 divided by e to the t dt. And I want to try to figure out what is f of 7. And so wherever I see an x, I'll put a 7. So I have the integral from 0 to 7 of t plus 1 divided by e to the t dt. And of course, I can't evaluate this definite integral because I don't know what the antiderivative of this thing is. It's not clear to me. But what I can do is I can use my calculator. So let me show you how you can use your calculator to do a definite integral without actually graphing the integrand. So what you can do is you can hit the math button and then scroll through here, and I have FNINT, which stands for finite integral, which is the definite integral. And then what you're going to do is you're going to put in the integrand. So I have left parenthesis x plus 1 on top, in parenthesis, divided by e to the t. So I put second ln, and I put an x there, in parenthesis. And now if you have an old school calculator like mine, you have to put a comma and then x. And some of you are going to have the newer version, which it will then just look just like this definite integral. So you just fill in the blanks. So I put an x there, then I put a comma, and then I had to say my limits of integration. So I go from 0, comma, to 7, in parenthesis. And then hit enter, and out pops my answer. And I'll round this to 2 decimal places. So it's approximately 1.99, I believe. Yeah, 1.99. And so that's my new function evaluated at 7. I get out 1.99. And I can do this for any number you plug in for x. I can use my calculator again and get a different answer. And what does this represent? Notice this is just the area underneath this curve. Right? So it's just 1.99 would be the area underneath this curve right here from 0 to 7. That's all that 1.99 represents. All right, let's do one last one, because once we create a new function, of course, we want to know what it looks like. How is it changing? So one of the points to calculus is it allows us to tell us if we have a function that's modeling a situation, we can use calculus to figure out how it's actually changing. Later on, when you get to differential equations, you actually create the functions themselves. And it's, in some sense, you'll kind of know the inverse. You'll know how a function is actually changing, and you want to find that original function that gives you that sort of change. And so we would like to be able to graph this. We basically like to be able to do what we've done before with other functions, and that is determine where the function is increasing, decreasing, concave up and concave down, find any local maximums, minimums, and inflection points, and then finally sketch the graph. And we're going to use the function we just did. So we're going to use this f of x equals the integral from 0 to x of t plus 1 divided by d to t dt. And if you think back, how do we do this? And hopefully you're thinking 4 steps, because that's what we're going to do. We're going to follow this 4-step process. And then in the end, we can come back and we can graph this thing. So we have step 1, which is find the critical points. Of capital F. All right, that's when f prime of x is equal to 0 or undefined. And so we take the derivative of this thing, so f prime of x, and the second fundamental theorem of calculus says, hey, you just plug in x wherever you see a t there, so you're just going to get x plus 1 divided by e to the x. And this is defined everywhere. Because remember, the only times you're going to have issues is if 1, you have 0 in the denominator, so you don't want that to be 0. Or 2, if you're taking an even root, you need to make sure that's bigger than or equal to 0, or we deal with complex numbers. And 3, the ln function can only take in things that are positive. So we don't have ln's, we don't have roots, but we do have a denominator here. And our denominator is e to the x, but e to the x is never 0. So it's defined everywhere. And then we're going to set it equal to 0. So take x plus 1 and set it equal to 0. Divided by e to the x, set it equal to 0. If you multiply both sides by e to the x will go away, and this implies that x plus 1 is equal to 0, which implies, of course, subtract 1 from both sides, so x is equal to negative 1. All right, so we have one critical point at negative 1. And so now we're going to do step 2. And step 2 is simply just do a sign diagram for f prime. And so here's my sign diagram. I have a critical point at negative 1, and this is for f prime. And the analysis is going to work for f. And so you just choose a point, like do f prime of negative 2. Point to the left of negative 1, and then a nice point to the right of negative 1, like f prime of 0. That's probably the easiest one. And you simply plug this back into f prime. So negative 2 plus 1 divided by e to the negative 2, which is equal to minus 1 over e to the negative 2, which actually equals negative e squared, because if it's negative, you put it on top. The exponent's negative right here. And so that's a negative number, so f prime is negative to the left of negative 1. And now I plug in 0, and I get 0 plus 1, e to the minus 2. I'm just plugging in, remember, for x right here. This is negative 0. And so that's equal to 1 divided by e to the negative 0 is just 1. And so that's equal to positive 1, and so it's positive here. This tells me that f is most likely decreasing, and then increasing. And then I also have a minimum here at negative 1. And now we can do step 3. And I'll write down the analysis where it's increasing, decreasing. It has local maximums and minimums in the end. So now we do the same thing, but now we want to find the critical points, not for f, but for f prime. So find the critical points. For f prime, that means f double prime of x is equal to 0 or undefined. And so to do this one, we're going to have to use the derivative we found, which is right here. So here's my derivative. And so if we do that, we'll have f double prime of x equal to, and this is going to be a quotient rule, so we have low, which is e to the x, d high, which is just a 1, derivative of x plus 1 is just 1, minus the high, which is x plus 1, times the derivative of low, which is just e to the x, and of course all over my low squared. So e to the x, I need some more room here. So all over low squared, so that's e to the x quantity squared. And so on top, I'm going to get this to be equal to, I have e to the x minus x plus 1 e to the x, all divided by e to the x quantity squared. I can pull out what they have in common, so they have an e to the x in common, so I have e to the x times, I put a 1 here, minus an x plus 1, all over e to the x quantity squared. And I'm going to get some cancellation here. This is going to equal, so one of these e to the x's on top is going to cancel with one of these on the bottom, so that's going to be a 1. And then I have 1 minus 1, so those ones are going to cancel. I'm going to get minus x on top, all divided by e to the x. And now I move on. Oh, not move on. So now, this is defined everywhere. So I don't have to worry about it being undefined. So it's defined everywhere. Why is it defined everywhere? Again, it does have a denominator, but the denominator is e to the x, which is never 0. There are no square roots, right? No even roots, and there are no ln's. And so now I'm going to set it equal to 0. So negative x divided by e to the x equal to 0. So multiply both sides by e to the x, and so this implies that minus x that will then be equal to 0. And this implies multiply both sides by negative 1, x is equal to 0. So x equals 0 is a critical point for f prime. And so now I do the sign diagram for f prime. So step 4. F double prime. And so we draw a nice looking line. We put a little 0 here. This is the sign diagram for f double prime. We're running the analysis for f. And I pick a nice point to the left. So let's do f double prime of minus 1. And let's do f double prime of 1. And we're simply plugging back into the original. Oh, not the original, but I'm sorry. The second derivative right here. So plug into here. And we have minus, or negative, a negative 1. Divided by e to the negative 1. And so that's equal to a positive 1 over e to the negative 1, which is just equal to e, which is like 2.718, blah, blah, blah. So it's positive here. And then when we plug in 1, we get minus, or negative 1 divided by e to the 1, which equals minus 1 over e, which is negative. And so we know, since the second derivative here is positive, f must be concave up. Here it must be concave down. And most likely we should have an inflection point right here because we have a change in concavity. So now I can write up the analysis for this. So let's zoom out a little bit. All right, so let's zoom out a little more. All right, so here are all the steps. And now I want to write up exactly where it's increasing, decreasing, concave up, concave down, local min, local max, inflection points. And I also then want to finally graph this thing. So on here, zoom out a little more, extend the page. Here we go. Okay. So right here, what do I know about f? And let's use a different color. Let's use blue. And so on this blue, what I know is that f is increasing, and I look up here, it's increasing from, well, -1 all the way out to infinity. So from -1 to infinity. And then it's decreasing from -infinity to -1, right, to -1. And it has a local minimum, it looks like, at -1. So local min at, and right here I can put what? I can put f of -1, which equals, so that's equal to the integral, and we have come back up here, and you can look at the original problem, so it's equal to the integral from 0 to -1. So it's equal to the integral from 0 to -1 of t plus t e to the t dt. And I can use my calculator to solve this, so I already have that last answer in there. So I'm going to just change this, hit second, enter, and instead of going from 0 to 1, it's going to go from 0 to -1, in parentheses, enter. And I get out about -7.2. So this is approximately negative, let's just do it down here. So approximately -0.72. And so there's where I have a local min. And then I want to do concave up and concave down. So f is concave up, and I look over here, and it looks like from -infinity to, or -infinity to 0 right here. So -infinity to 0, it's concave up, and it's concave down from 0 to infinity. And then it has an inflection point. Right, so inflection points, let's write INF point. At what? At 0, comma, f of 0. And so that's equal to 0, comma, and this one's actually really easy. F of 0 is the integral from 0 to 0 of t plus 1 e to the t dt. And I don't need to use my calculator to evaluate that because I'm going from 0 to 0. And now think about it. What's the area under nothing? Right? If you're going from 0 to 0, there's nowhere for me to go from. I'm just start at 0 and I end at 0. So the area is 0. So this is the integral. This is the point 0, comma 0. Okay. Once I have this information, so I have all this information right here, I should be able to graph it. So let's graph this thing. And when I graph it, let's use black, and let's zoom in just a little bit more here. So I can make a little bit more of a room here. So I want to graph this thing, so I'm going to graph it right here. And what you want to do is you want to plot the important sort of points here. And so I know that there's a local min at -1, or -1, negative 0.72. So let's put that right here. So this is a min. And it's at what? This is about 0, comma, negative 0.72. And I have an inflection point at 0, 0, so INF point at 0, comma 0. And I want to connect them so it's increasing from, oh, and this is -1. I'm sorry, I don't know why I put 0 here, but this was supposed to be -1. And so I know it's increasing from -1 to infinity. I know it's decreasing from -infinity to -1, and I have an inflection point here. I'm concave up, and I'm concave down. So I would guess concave up, and then concave down. I would guess it looks something like this. And so we can use our calculator to check our answer, but I want you to notice when I put this in my calculator, it's going to take forever for it to do. So we'll get it started, and I'm going to pause the video, and you can watch yours, and I'll start mine up when it gets the answer. So on this one, what do I have? I have to hit math. Okay, so remember, I'm trying to integrate the function they gave me. So I did the integral, left parenthesis, x plus 1, in parenthesis, and then divided by then second ln to pull up the e to the x. So there's the integrand in parentheses there. And then comma, I'm integrating with respect to x, so I put an x here, comma, and then I'm going from 0 to x. So there's my function in parentheses. And now for my window, since I know I have a minimum at -1, I'm going to start at -2. And then since I have an inflection point at 0, oops, I guess I hit something wrong, so go to, so -1. And then since I have an inflection point at 0, input 0, I'm going to put 1, just a little bit to the right. And then I'm going to hit, oops, this should be -2, right? So -2 to 1, and then hit zoom, zoom fit. And I'm going to pause this because it's going to take forever, and I want you to see how long it takes your calculator to do this. And so there it is. I clocked it at about 2 minutes, but I'm using my desktop, and I think it has probably more processing power, so it goes a little bit faster. But there it is. And so you see it looks basically exactly the same. You have your minimum here, which you can test. You know, you can hit trace and -1 and see what's going on. And so you can see that's right. You know, you hit 0 and see it pops out 0. Now, trying to graph this from the beginning, if you don't know where to look, you won't get anything. And anything that you could actually recognize, you have to know where to look. In addition, this function takes so long to graph that by sort of guessing and checking, you could use up 10, 20 minutes at a time on a problem that should take you, maybe 5 minutes, 10 minutes at max to do properly. Right, so these are really nice little problems that you'll see at least one of these on the final, most likely. All right, I'll see you guys tomorrow.